So divide and conquer in visual question answering. So at this point, I don't need to say that VQA is an amazing task. Attracted a lot of actually us working on it from a variety of different aspects, and very quickly actually the community started working on it. Less than a year, maybe we have a benchmark, we have half a dozen of data sets, we have maybe a dozen of different algorithms, we have a challenge. It's just amazing. What excites me about VQA more than everything else is actually the coverage. It's very, very, very broad. In fact, almost everything that we do is a form of VQA, right? So when we talk about many of the tasks that we do is a form of VQA. And that's basically, it's very exciting, and at the same time, it's very concerning for me. The fact that it's concerning for me is that how can we maintain enough of a coverage for such a broad task? And let me show you this picture. So with this picture, so many of us have seen results like this. If I ask a question like, what color is the cup? I think there are many sort of existing state-of-the-art question answering algorithms that will answer the question. But the minute I actually start asking more interesting questions like, what happens if I push this cup? Well, we tried a bunch of different state-of-the-art algorithms, among which there were the ones that had the code released or let us play with their code, and this is basically the result that we got. So what happens if I push this cup? McDonald's, Starbucks, Hello Kitty. And we thought that maybe actually we're not being explicit about the question. Let me just switch the mic. Okay, so the questions were McDonald's, Starbucks, and Hello Kitty. Then we thought, okay, let me specify the questions more carefully. So we changed the question to what happens if I push the cup toward the edge of the table. That's more concrete, and I actually sort of know what to expect as the answer. And the answers was much better actually this time. No, yes, 0, and orange. So this is funny, but actually it's not a surprise, right? Because the data sets on which we train these models, they don't have examples like this. So we shouldn't expect those models to be able to answer questions like this, and that is exactly my point. So how should we make a broad enough visual question answering system that can cover a wide spectrum of algorithms? And there are two schools of thoughts. Actually, before going there, let me show you a more exciting example. I'm not going to show you the answers on the questions. They were embarrassing, even to myself. For this image, the question was if the candle is going to actually is going to lit or is going to die. And do we know the answer? My answer was obviously it's going to get into the water, it's going to die. But it turns out that it's actually going to continue to live. You hear me? Is that better? Okay, so there are two basically, and the problem gets harder and harder. So this was basically the thing that gave the example that gave me a nightmare. So the question is, what's going to happen to the board? So there is a board, there is a piece of, there is basically a fire under a string, and the question is that what's going to happen to that wooden platform? Just imagine how much do I need to know to be able to answer that question. I need to know that actually fire is going to sort of cause damage to the string. I know that when the string goes, this thing might actually move this way, and as a result, the wooden platform might go in the opposite direction. So when I was looking at this, it turns out basically it was sort of clear to me that this is hard. There's so many things that I need to actually deal with to be able to answer questions like this. And so a typical solution to this, I basically would imagine there are two schools of thought on this problem. The first one would be, well, I'm going to continue what most of VQA systems as is right now. I'm going to do a direct approach to the problem. And a direct approach would be, well, let me just grab as many exciting examples as I can, and I'm going to basically just do what I want to call reasoning by template matching. It's basically, I'm going to have my standard CNN, LSTM, attention, without attention, and many different versions of those that we are all aware of. And I'm going to basically do a direct approach to it. So that's one scenario to be able to deal with this problem. The other scenario that I'm actually sort of appeals or I like better is the approach of sort of dividing the problem into pieces. Why? Because I was sort of expected to generalize, and so this divide and conquer problem sort of seems like the right problem. I actually don't know the right answer to this. I'm just dividing what's out there, And I myself would like the one on your right better than the one on your left, mainly because I actually don't know how can I grab enough training data for a direct method. So now the problem is that, so I know that basically many, we have seen throughout maybe 20 years, many systems that show some sort of generalization, they all benefit from a version of this divide and conquer. So I'm going to need to break down the problem into different pieces, and those pieces might be something that's A, learnable, and that should be reusable for me. And after that, I need to put them together, and for the lack of a better word, let me call that reasoning. So what should I do? So if I want to actually break down the problem, what should I do? And so sort of I was thinking about the components that exist. Basically, I remember the famous Jitendra's talk on 3 R's of computer vision. And I thought there might be actually 3 R's of visual question answering. And there are actually, in fact, there are 3 components of visual question answering. So we have a question, we have visual data, and we have an answer. And my 3 R's of visual question answering would be the interpretation, well, sorry, it doesn't have R, the extraction, but I have 1 R, the reasoning part. So basically these are the 3 components that I think or naturally exist in any question answering system, sort of a typical natural approach to that. I need to understand the question text, I need to extract useful information from the image, I need to put them together somehow. And when you think about those direct approaches, they're doing all of them actually. And in some sense, the direct approach might be even simpler. It's easier to train. I don't need to worry about what are these elements. How should I deal with them? How should I deal with their interpretation, with representation? Do I need to learn them or not? So in a sense, direct approaches are much easier. They're joined, so I can train all of those together. But the problem is that I'm worried I cannot actually give them enough data to maintain the coverage that I want. And if I want to actually maintain the coverage that I want, so the question is, how should I do that? And the strategy that I like is sort of divide and conquer. I want to break down the problem. I want to break down the problems into different pieces and sort of try to learn those pieces, put them back together. So if I want to break down the problem pieces, what are the things that I should break down? Well, one natural thing would be, maybe I should break it down based on the question type. What kind of questions I'm answering? If they're asking about where is something, maybe I can use a detector. If it's asking about the color, maybe I should use an attribute, and so on. So that's one natural approach. The other would be maybe based on these 3 components that I was talking about. The other very, very challenging question is basically, to what granularity should I break down these problems? And what would be the right representation when I'm actually breaking these down? Because eventually one thing I can do is I can actually go back to hardcore old school AI, where I have formal semantics, and I can actually do an honest, true reasoning over those formal semantics, but I know that basically there are difficulties there. So what would be the right level of granularity, what would be the right representation, and eventually even if I have those and if I have the knowledge that I need, how can I perform reasoning over that? So is this actually even possible? So let's go back to these 3 pieces again. So the interpretation, the extraction, and reasoning, and let's start breaking them down. So if I only look into understanding the question, that's already actually well defined within the LLP community. We actually have sort of formal semantics for them. We know how to represent them. We know how to deal with them. We know what are the learnable and reusable pieces. So we can actually do that in isolation. That's one way of actually breaking down one of those pieces. So Trevor's talk before, it's one of the papers that Trevor was talking about, the decomposable models or the modular networks, are examples of sort of decomposing it and breaking it down. These 2 parts together maybe. So interpretation and reasoning together. You can break it down into these AND modules, the FIND modules, and all of those actually have a version of formal semantics attached to them. It might not be the most formal semantic, but it's sort of an informal formal semantic attached to each of those components. That's actually very exciting. Why? Because then this allows us to actually break it down into pieces that I can reason over. So what I'm going to be talking about is actually sort of break down into this part of it. So given an image, how should I break it down into pieces that are reusable and that I can actually use it for later stages? So this is not news to us, so we've seen many different ways of breaking these down, attributes, detections, classification, pose estimation. All of them are examples of actually breaking down the visual extraction part. I'm going to actually talk about one of those, actually 2 of those, that sort of excites me these days. One of them is, how can I break down the space of verbs for visual question answering I know that actually I need to understand verbs to be able to answer many of the questions, at least in the VQA dataset. They're asking about the objects being manipulated. They're asking about the agent. They're asking about the place. They're asking about the effect of an action. And I need to understand all of those. So how should I break down the space of verbs in a way that I can actually have a close to a formal semantic representation for verbs? So it turns out that folks in NLP, again, have already thought about this problem. So semantic role labeling is an example of that problem. This is in fact exactly breaks down the space of verbs for us. It will define verbs as functions, where the functions are basically defined, where those functions takes arguments. For example, for a sentence, a boy fixing a car with a tire iron and a strip. So you can detect the verb, you can figure out the agent, you can figure out the object, you can figure out a tool, and you can figure out a place. And that's sort of the exact kind of semantics that we do need for understanding and summarizing some sort of actions or images that depict a form of action. And that's what we wanted to do. We wanted to sort of figure out how can I break down the space of verbs. Well, it turns out that FrameNet and many other resources have already done that for us. So FrameNet is an ontology of many thousand verbs, more than what they can actually deal with in images. So what Mark did at European AI2 is actually he went down and sort of defined this problem of situation recognition. So his problem is that from an image, how can I predict not only the verb, but all of those semantic interpretations of that. Remember, this is actually a structure that summarizes what's happening in an image. Not only do I need to predict a boy fixing, but I also need to understand that the role of the boy is the agent of the verb fixing. The tool is actually a tire iron. And the object of this verb is a car. So I need to figure out how I'm going to deal with this problem. So what Mark did is sort of, first of all, we needed the data sets of these kind of structures. So he collected a data set. It's called in situ. It's available at insitu.org. Actually, check it out. So it has something in the order of 130,000 images annotated with more than 500 verbs. So there are 2,000 rows in the data set, something in the order of 12,000 nouns in the data set. And this is an example, basically. We have a verb, we have the rows, and we have the instantiations of the values in the row. Now that I have this data, I can actually start and sort of try to predict a structured output from an image. So what we did was basically something fairly straightforward. You have a deep learner, you put a CRF on the top of it. You just need to be careful how to propagate the gradient from the CRF to your network. And at the end, what you're going to get is basically sort of a structured prediction, a joint prediction of all of those verbs, roles, and the values associated with each of those slots. So here are some examples of what Mark's system can actually produce. For the image in the right, let's say, it's basically not only it can say it's falling, but it can actually say that the agent of this verb is a person, is coming from a horse to a ground, and it's happening in a field. Or a person is sort of spearing a fish in an ocean. So this is sort of a kind of very, very rich understanding of what's happening within an image, and it's very suitable for actually answering questions about what is this happening. For example, so the razor over here is actually very, very small, but Mark's system can actually predict the razor, despite the fact that very few pixels actually correspond to the razor. It's just because basically you put all of those values together in a structured way that enables you to predict this whole structure. So this is basically what excites me most about this is sort of the generalization capability. The fact that his system can actually predict instantiations that didn't exist in a training set before. So in his training set, he has 35 instances of actually people feeding milk to babies, people feeding carrots or other things to horses, but no instances of people feeding milk to horses. And I can correctly predict that. Or no instances of actually having monkeys hugging cats or dogs. What is that? Dogs, and being able to predict actually who is hugging what. So that's sort of one example of these sort of intermediate, formal semantic representations that I'm talking about that can actually work as sort of an intermediate step in our visual question answering system. So his data set is available at insitu.org. He has actually a very cool live demo. Play with it and it will surprise you how well it works. So you can get the code, the data, you can browse through the data, all of them over here. So here's one example for me that we're basically was talking about how can I break down the space of visual knowledge, visual information extraction. So another example I want to talk about is sort of a different kinds of question answering it on diagrams. So we've seen in VQA there are abstract images. So what this was actually Ani, Eric, Mike, Minjun, and Hannah did was basically they went through and studied the problem of actually understanding diagrams and answering questions about diagrams. Why diagrams? Haven't we solved this problem 20 years ago? It turns out that no. And diagrams are very interesting. So to me they're interesting for two main reasons. One of them is that a significant portion of visual data available online is in form of diagrams, and we sort of neglected processing them. The other interesting part for me is that diagrams sort of show very complex phenomena that I cannot find an image to depict. Think about a water cycle or a food web. I cannot find a single image that depicts a food web or a water cycle for me. So in some sense they're easier than images in terms of segmentation, processing. In some sense they're actually harder than images because reasoning over them might be harder. And that might be actually a nice test bed for me to test how well I can reason about diagrams. So here is basically an example of a diagram question, and the question is basically which element is a carnivore over here. Again, remember, how much do I need to know to be able to answer this question? I need to know that this is an entity, this is an entity, this arrow over here means eating, and if this eats this, and this is an animal, therefore that's a carnivore. So again, the question was, what are the formal representations for diagram understanding? And it was actually turned out to be hard, but we sort of found in graphics community people already defined that for us. So we sort of used what they defined to be able to give again an example of a formal semantics. So to an old school AI person, these are not formal semantics, but these are sort of somewhere in the middle, from sort of a completely implicit representation toward a completely semantic representation. So these are sort of standing somewhere in the middle, and we should be able to use those. So what we did was sort of we collected this data set. This is basically a very densely annotated data set of diagram elements with all of those relationships together. So some of us actually call this shining data set because of the pain and suffering some of us have gone through to create this data set. It's basically big data sets of diagram elements, relationships, and what does what with what. So it's basically a very rich data set, and it has very complicated questions. For example, so if what happens if from the above food web diagram, what will lead to an increase in the population of deers, increase in lions, decrease in plants, and all of those things. And remember, I need to know a lot about diagrams, especially if I want to actually deprive myself from seeing examples of these food webs in my training set, and that's basically what I want to go with. So how do we approach this problem? So people in graphics community already defined the formal representation for us, so we use that to build our model. So we have sort of a representation that tells us what is where and what is connected to what in what way. So we have, again, for the sake of time, I don't go to the details of that. So we have sort of a sequential model that can handle those kind of sort of parses. It adds to the diagram parse one by one as it sees. It can does some versions of contextual modeling as well. Here's an example of basically a diagram parse that it can produce. It will basically tell you what is where and what is connected to what. And again, the reasoning is another hard problem that we need to do. But now, what happens is that now I have my formal representation. So I might be able to actually do standard reasoning tricks over that. So what we did was basically we did something similar to a memory network architecture, where we actually have an attention mechanism, and instead of actually attending on pixels or regions over an image, we're actually attending to the facts extracted from our previous network. So that means that in what part of this parse graph should I attend to be able to answer that question? And it turns out that, again, for the sake of time, I don't go into details of that, we can answer some sort of simple questions, but not the ones that I was hoping for, the ones that requires deep reasoning. Why? Because actually some part of it is missing, and that missing part to me was the reasoning part. So it turns out that memory networks and the likes with the attention are not powerful enough to actually do deep reasoning, but that's sort of an exciting next problem in visual question answering. How can I do actual reasoning? But one side effect that was exciting for me was this. Ignore everything but this blue and yellow chart. So this is sort of a comparison between an explicit representation versus an implicit representation. This is basically, we worked really hard to get this number high. because at the beginning we thought that would be our approach. We actually sort of plotted at some point, and we realized that we actually do need this form of representation. And this non-trivial gap between these two numbers sort of shows me the benefits of having that intermediate representation. Let me quickly shift the gear and go to the third part. And the third part is basically how can I reason? So how can I actually sort of start breaking down this space of reasoning? This is hard. So we don't know how we can formally break down the space of reasoning. But I'm going to show you basically a couple of things that we did in the space of reasoning. One of them is sort of what Roosevelt, Sam, and Mohammed did in sort of physics-based reasoning. So the question is, how do I know that where the ball goes in this picture? If I ask any of you, you have a clear understanding of where this ball goes. Well, you've seen it before, you have a lot of context, you know that this person is hitting it, all those folks are looking at it. So this would be sort of, I know where is the direction of the force, where is the direction of the velocity, so I should be able to learn these kind of things. And we sort of make one step toward being able to reason about that. It turns out that actually it's hard to do it directly in real images because the data problem is a problem. So what we did was we sort of defined Newtonian scenarios. These are examples of the things that high schoolers learn about Newtonian physics. And what we did, aside from that, is for each of those Newtonian scenarios, we actually compiled a data set of images that corresponds to that, a wide variety of different things, coupled with game engines videos of those. So for each of those, we have multiple different game engines. We asked Turkish to annotate all of those for us. So I have an image, a bounding box, what category, what Newtonian scenario it belongs to, an exact motion of the object in a game engine. So now the problem of predicting where does this ball go, given this image and this bounding box on it, so it would turn out to be which Newtonian scenario it is, and if I figure out which Newtonian scenario it is, can I figure out what state it belongs to? And if I could figure out what that state, then what I can do is I can sort of go to this very, very rich space and sort of just borrow the information that I want, because that's sort of in the middle of a game engine. I know the force, I know the velocity. I should be able to just grab those, superimpose it over here, and then I know where this ball goes to. How do I do this? So it turns out all I need to do is sort of learn to correspond actual images with bounding boxes on them to states in game engines without having a supervision of the states. We have this Newtonian neural network. I don't want to talk about the details of this, but at the end of the day, you will basically learn how things move based on a correspondence from a game engine video. And now, given one single image, a bounding box on an image, we can predict where things go based on this correspondence problem. So these are small pictures, but let me show you some of the cool stuff that Roosevelt and the folks did. So for this image, we asked the system, where does this object go? And the answer is basically this way. So for this system, we asked, where does the ball go? And the answer is this way. We asked, where does the car go? And the answer is this way. Notice that now my question and answers are not in natural images anymore. So it might be actually in semantic representations themselves. So this is sort of a different kind of question and answering, where the question and answer might not be in text. Where does this guy go? This way, and of course this guy is going to do this. Believe me, it's going to do that. We tested it. So this one, our network actually failed to recognize that this is sort of a slanted surface, and it failed to match to the right Newtonian scenario. So now, based on this sort of physics-based reasoning, what we can do is we can actually figure out the force and the velocity vectors, and we can reason about them. We can reason about no motion, for example, for this chair over here. We can reason about friction. We can reason about gravity and all the velocity vectors and force vectors that apply to an image. Then Roosevelt actually, Mohammed and Abhinav actually extended it further down, and they decided that actually we want to study this in an active setting, where the question itself might be something in the form of what I showed at the beginning of my talk. What happens if I push the cup toward the edge of the table? Again, we cannot study in real images. I really wanted to do this, but that's not possible. We cannot afford breaking so many things, and we cannot actually enforce enough of variance that we can do this. So we started sort of converting this again to game engine. So we went to SunRGBD. We sort of reconstruct all of those scenes in a game engine, again in the crudest possible way with boxes. And once I'm in the game engine, then I can actually apply forces to things and watch what happens. So then it was basically sort of free for us to generate as many samples as we want about where things go if I apply specific forces to them. So then we build this sort of LSTM, weird LSTM, that given a single image and a specific force then our system can actually predict a variable size sequence of directions where things go. So here are some examples. For example, how much time do we have? Okay. So let me just show you a couple of actually cute examples in the video. So these here are examples of actually how things move when we apply forces to them. So given this image, we ask the question of how does this move when I apply this force, and here is basically our understanding. This is the output of the LSTM on how things move when I apply a specific force to them. So the next one is sort of actually exciting for me because it actually learns about things bouncing from each other. So this would basically tell us that if you apply a force, it will hit that object and bounces back. Well, how do we learn this? Because it basically rendered a lot of scenarios in the game engine. We should be able to sort of predict how things behave. I'm not gonna be able to push wall. If I push other stuff, they might actually bounce to each other and things like that. Things don't go through each other. Information like that from sort of basically observing a lot of game engine. So just to be in time, let me sort of conclude. So I like to think that so one of the leading approaches to question answering would be a version of divide and conquer in terms of how to break down the problem. It would be a decomposable network. It would be actually multiple different reasoning in the form of an expert system. It would be sort of a version of sort of seeing different pieces of the problem. And the community, I believe, have already started actually thinking about it. Accounting network and all of those actually are examples of these little pieces that we need to solve before being able to actually solve a wide range problem. And I do believe that basically this informal formal representation or informal formal semantics would be probably the right intermediate representation for our deep models. With that, I stop.